If there's any radical technology prediction, the point isn't that it was a few years delayed, but rather that it happened at all, sending shock waves through the EV industry. Tesla's new motor, with groundbreaking advancements like the interior permanent magnet synchronous reluctance motor, carbon-wrapped Plaid motor, and flatwire winding, is pushing efficiency, power, and performance to unprecedented levels. Elon Musk has expressed confidence that this year the solution will be achieved. But what exactly is Tesla solving, and how does this new motor set a new standard for electric vehicles? Let's explore the details of this game-changing innovation. Before we get into it, please subscribe to AutoFusion and help us achieve our goal of 111,789 subscribers. Tesla's move from induction motors to permanent magnet synchronous motors marked a key moment in its EV technology. While induction motors, such as those in Tesla's early models like the 2008 Roadster, offered impressive performance, their inherent limitations made a switch inevitable. The Roadster's three-phase AC induction motor, based on the Lotus Elise design, delivered up to 185 kW of power, a maximum speed of 1,400 revolutions per minute, and an impressive torque of 430 Nm. Similarly, the first Model S and Model X used three-phase induction motors with outputs of 215 kW and 370 Nm, keeping the Roadster's top speed of 1,400 revolutions per minute. These motors offered high power density and acceleration, but at the cost of reduced efficiency at low and medium speeds. In 2014, Tesla took another leap by introducing copper rotor cage technology, which enhanced the power and efficiency of induction motors. This development allowed the Model S Plaid to achieve jaw-dropping acceleration, reaching 100 km/h in just 2.1 seconds, and a top speed of 320 km/h. Despite these feats, the reliance on copper windings and the lack of permanent magnets in induction motors made them less energy efficient for mass-market vehicles like the Model 3. But why did Tesla continue using induction motors even as manufacturers in China switched to lighter permanent magnet synchronous motors? The reason lies in cost and reliability. Permanent magnet synchronous motors rely on rare earth materials like neodymium, iron, and boron, which are expensive and thermally sensitive. On the other hand, induction motors do not need permanent magnets, removing concerns about demagnetization at high temperatures, which is critical for maintaining long-term performance and reliability. Induction motors use copper rotor cores, a cost-effective and durable design that ensures stable performance without the risk of magnetic degradation. However, this affordability comes at a price. Induction motors are less efficient at lower speeds and prone to rotor overheating, limiting their efficiency in EV applications compared to permanent magnet synchronous motors. Recognizing these limitations, Tesla began shifting to embedded permanent magnet synchronous motors in its third-generation drivetrains, first seen in the Model 3 and Model Y. This transition allowed Tesla to boost efficiency and range while addressing the thermal and performance challenges posed by induction motor designs. It marked a crucial advancement in drivetrain technology. Enter the interior permanent magnet synchronous reluctance motor. Tesla's new motor embeds powerful neodymium magnets inside the rotor, significantly reducing energy losses and improving efficiency, especially at low to medium speeds, where induction motors tend to fall short. Additionally, permanent magnet synchronous motors are more compact, lighter, and require less constant current to generate a magnetic field, making them ideal for range-focused vehicles. Now let's take a look at what's new in Tesla's motor technology. Tesla's latest motor innovation, highlighted by the Plaid carbon-wrapped motor, represents a revolutionary step in electric drivetrain design. Elon Musk revealed that this new motor is not only smaller and more powerful, but also capable of reaching extremely high rotational speeds. The innovation stems from the use of carbon fiber winding around the rotor, a process enabled by Tesla's in-house developed advanced machine automation. This process ensures that the rotor remains under precise compression, addressing thermal expansion issues that could otherwise cause the carbon sleeve to loosen in colder temperatures. The benefits of this new design are groundbreaking. The carbon sleeve allows for a significantly stronger electromagnetic field than traditional steel-encased rotors, enabling the motor to achieve much higher revolutions per minute while maintaining structural integrity under immense centrifugal forces. As a result, Tesla can push its motors to performance levels that were previously unattainable. The Plaid motor, small enough to be lifted by a single person, delivers unparalleled power and efficiency. Musk has referred to the Plaid motor as arguably the most advanced motor on Earth, but hinted that Tesla is already working on an even more powerful version for the next generation Roadster. In addition to the carbon-wrapped motor, Tesla has also revolutionized motor technology with flat-wire winding. Introduced first in the 3D6 motor used in the 2022 Tesla Model 3, this technology marks a significant leap over previous motor designs. Instead of traditional round wire coils, flat wire coils deliver higher power and torque densities. The results are remarkable. The 3D6 motor achieves 900 revolutions per minute and 440 Nm of torque, outclassing earlier models. Flat wire technology offers significant advantages compared to round wire motors. By increasing the slot fill rate by 20%, the motor size can be reduced while still maintaining high performance. The broader cross-section of flat wires decreases resistance, reduces heat generation by 50%, and lowers temperature rise by 10%, all of which improve overall efficiency. The flat wire motor achieves a power density of 4.4 kW per kg, a major improvement over the 3.2 to 3.3 kW per kg density of current round wire motors. Since copper loss accounts for 65% of motor losses, reducing winding resistance in flat wire motors significantly lowers these losses, further boosting efficiency. The Model Y, which features a flat wire motor, exemplifies these advancements. It optimizes motor volume and power density with the maximum power of its permanent magnet synchronous motor rising from 202 kW to 220 kW, and peak torque increasing from 404 Nm to 440 Nm. The rear motor weighs only 5.78 kd, ensuring uniform and strong welds while reducing the rotor's volume and weight. With these advancements, it's expected that the Model 3 will soon follow suit, as Tesla accelerates the adoption of flat wire motors across its lineup. Other automakers, including BYD, IO Ideal, and Volkswagen, are also transitioning to this cutting-edge motor technology, signaling its potential to become the industry standard. Oil cooling technology is another significant development in Tesla's motor technology. By switching from water cooling in the early Model S vehicles to advanced oil cooling in the Model 3, Tesla has significantly improved thermal management and power density. Unlike water cooling, which only cools the motor casing, oil cooling directly targets the stator and rotor, providing far superior efficiency. This shift has allowed Tesla to tackle thermal limitations more effectively, unlocking greater performance. Now, let's consider what motor configuration can truly balance performance and power. Tesla's revolutionary interior permanent magnet synchronous reluctance motor is the key to striking that balance between efficiency and performance. This motor combines the compactness and efficiency of permanent magnets with the brilliance of reluctance motors. IPM, interior permanent magnets, refers to the embedded permanent magnets within the rotor, while synchronous, SP, signifies its synchronous nature, and reluctance, res reluctans, refers to the motor's reliance on magnetic reluctance for torque generation. Why did Tesla choose this configuration? The interior permanent magnet synchronous reluctance motor offers distinct advantages, particularly at low to medium speeds, which makes it ideal for mass-market vehicles like the Model 3. Since the Model 3 prioritizes range and efficiency over extreme torque, this motor configuration is a perfect fit. However, Tesla's premium models, like the Model S and Model X, rely on induction motors due to their ability to handle high torque demands, faster acceleration from 0 to 100 km/h, and sustained high-performance operation at elevated temperatures. The interior permanent magnet synchronous reluctance motor is not without its challenges. Permanent magnets are prone to demagnetization under high temperatures and heavy vibrations, even at low speeds with high torque. The strong electromagnetic fields created by the stator can induce eddy currents in the rotor, which causes magnet degradation. Tesla addresses this by embedding the magnets inside the rotor core, rather than attaching them to the surface. This design minimizes the risk of demagnetization and improves durability, allowing the motor to perform well under challenging conditions. However, embedding magnets within the rotor introduces another issue. At high speeds, the magnets are located close to the stator coils, and as the motor spins, the strong magnetic fields generate significant reverse electromotive force, back EMF. This back EMF opposes the driving voltage in the stator coils, requiring much higher driving voltage to maintain performance at higher revolutions per minute. To solve this, Tesla employs advanced control systems that continuously detect the rotor's angle and speed, calculating the voltage, current, and phase of the stator's three-phase electromagnetic field to ensure optimal performance. The interior permanent magnet design not only enhances the mechanical strength of the motor, but also improves performance by managing heat more effectively, preventing the magnets from detaching at high speeds. Tesla's synchronous motor features 6 V-shaped axial slots with powerful rare earth neodymium iron boron magnets embedded in these slots. This configuration, known as interior permanent magnet, IPM, divides each magnet set into 2 parts, further splitting each part into 4 smaller sections. This segmentation significantly reduces eddy current heating, resulting in better thermal efficiency and reduced energy losses. This innovative design isn't unique to Tesla's Model 3. Nearly all synchronous motors in EVs and hybrid electric vehicles adopt a similar approach, though the specifics of this technology, such as the size, position, shape, and quantity of the permanent magnets, vary between manufacturers. These details remain closely guarded trade secrets, underscoring Tesla's unique engineering expertise. Do you think Tesla's new motor will make a noticeable difference in your driving experience? Comment 1 if you believe it will make your Tesla feel faster and smoother, or comment 2 if you think it won't change much for everyday driving.